So, welcome back to lectures on engineering mathematics 2. So, this is lecture number 20 on residue, and this is the last lecture on this module, complex analysis. So, today we will be talking about what are the residue and how to evaluate the residue, and the most important theorem of this topic is the residue theorem, which has application for evaluating several complex integrals. So, we will also cover some portion for this evaluation of complex integrals. So, coming to the residue. So, suppose this f z, a function which is analytic for all z except this z equal to z naught, which is an isolated singular point of this function f z. So, the previous two chapters where we have discussed the singular points and also the expansion, in particular the Lorentz series expansion, that will be very useful to discuss this residue now. So, the Lorentz series of this f z about this z equal to z naught, we can have such terms, so the positive powers and then the negative powers, and where this b n, this coefficient, we can compute with the help of such integral that was already discussed in this topic where we have covered the Lorentz series. And just to recall, we have mentioned there that this coefficient b 1, the first coefficient or the coefficient of this 1 over 1 minus z, there it is called residue, and now we will go more into the detail that what are different kind of how to evaluate residues, and then what are the applications of this residue. But this coefficient b 1 in this Lorentz series expansion, the coefficient of 1 over z minus z 0 is called residue of this f z at this z equal to z naught point, and remember this z naught is the isolated singular point of this z naught. So, now this b 1 here, which exactly or directly coming from this integral, it is 1 over 2 pi and f z, z minus z naught power this minus n plus 1. So, if n is 1, then this becomes 0. So, there is no term z minus z naught here. So, this is a simple integral for this b 1 equal to 1 over 2 pi I and integral f z d z. So, indeed this is exactly the point why we are discussing this residue here. So, if we take a look at this integral over this C, which is a curve which bounds exactly this point z naught, is equal to 2 pi I into b 1. So, many complex integrals which are complicated to evaluate, we can get the value with the help of this formula, which says that this integral is going to be 2 pi I into this b 1. So, if we can find, not using this formula naturally, this b 1, we will not use this formula, or in the expansion of also the Lorentz series expansion, if you remember, we did not use this formula to evaluate these coefficients, because computation of these complex integrals may be complicated. So, by some other means we have expanded the function in terms of the Lorentz series. Once we have the expansion, we can get the b 1, and once we have b 1, we can get this integral. So, it goes other way around. To evaluate this integral, we use this Lorentz series expansion, and then we can get b 1, and we have this integral ready. So, but there are other ways also to evaluate this b 1, the residue b 1. So, we will now discuss in detail that how to get the residue at a point z equal to z naught, which is a isolated singular point of f z. So, how to calculate the residue? First we will discuss this, and then later on using the formula we have just discussed, we will evaluate some integrals. If z equal to z naught is a removable singular point, and now the classification is coming into the picture. So, we have a singular point, and if it is a removable singular point, then we know that there is no term in the principal part of the Lorentz series expansion, and in that case if it does not have a principal part, it does not have a negative powers of z minus z naught. So, naturally this B 1 is going to be 0, and that means the residue is 0, which clearly says that this integral, the curve integral, curve is taken the curve enclosed, the simple closed curve which encloses this point z naught. So, this is going to be a 0 value of this integral, which is Cauchy integral theorem also can give us this result when we have a removable singular point. That is the important point here to be noted. The second one, if this point z equal to z naught is a simple pole, then how to get this residue? I mean, always we can get with the help of the expansion, but these are the some other ways where we can easily get these residues. So, if we have a simple pole, then how to get the residue? In that case, this is going to be the expansion, the Lorentz series expansion, which we have discussed before, that in case of simple pole we have only just one term in the Lorentz series expansion, that means B 1 over z minus z naught, and we are interested in what is this B 1. So, with the help of the limit, it is easy, because if we multiply here by this z minus z naught term, here does not matter, it will be just increase, and then this will cancel out. So, when we take the limit, this everything will go to 0. So, this limit will give us directly B 1. So, to get this B 1, we multiply this by z minus z naught and then take the limit z approaches to z naught. So, without expansion of this f z to the Lorentz series, we can get this B 1, which is readily given here. So, if it is a simple pole, we will just multiply by z minus z naught to this f z and take the limit, and whatever number comes, that is actually the residue. Now, if we have the pole of order m, so that means there are these first m terms in the Lorentz series expansion with B 1, B 2, B 3 and B m. In this case, what how to get the residue? So, how to get this B 1? So, again with the this limiting approach is going to help us. So, if we multiply both sides with z minus z 0 power m, so what will happen? We have this power m will increase here, and then this is going to be m minus 1, m minus 2, the last one will be just B m. So, this is the expression we will get for this one. And now, if we differentiate this m minus 1 times, so all these terms will disappear, only this term will come as a factorial m minus 1, and then we have here B 1. All other these terms will be 0, and from here we will get B 1 times this factorial 1, and here also we will get, because the m plus n, so more than m minus 1. So, here also we will get some powers of z minus z 0, but when we take the limit, this portion will become 0, and here we will get just B 1. So, the conclusion here is how to get this B 1 now. So, we have already multiplied, and if we differentiate m minus 1 times and then take the limit, so we will get exactly B 1, and this the B 1 there will be a term here with factorial m minus 1, that will go to the right hand side. So, we have to differentiate this m minus 1 times and then take the limit. So, we can get this B 1 directly if it is a pole of order m. Now, the residue at an essential singular point, that we have to basically use the Lorentz series expansion and then get the coefficient of this 1 over z minus z naught. Well, so coming to this important theorem, the residue theorem, though we have discussed that integral, that how that integral can be just evaluated 2 pi I B 1. So, just to recall, we have discussed that this f z is a single valued analytic inside and on a simple closed curve C, except at this isolated singularity z equal to z naught. In that case, we have seen that this integral value is nothing but 2 pi I b 1. This was the situation when we have just one this isolated singular point inside this closed simple closed curve C, but this can be generalized. So, this is exactly the residue theorem, but we can generalize this, that f z is single valued analytic inside a non simple closed curve C at an isolated singularities, except this isolated singularities z 1 z 2 z r. So, instead of one singularity z naught, we have these r singularities inside C, and in that case the result is just the 2 pi I and the sum of residues at these isolated singularities. So, we have r singularities, that means we have to get these r residues, and then we have to sum here these residues multiply by 2 pi I, and that will be the integral value over this curve which encloses all these singularities. So, we have this formula k from 1 to basically r, because we are taking z 1, z 2, z 3, z r, and then this residue and the value of this integral can easily be evaluated using this residue theorem. So, how this residue theorem is coming, we will give just some idea here. So, we have this f z function which has these singularities r singularities, that means this is the situation that we have a curve which encloses all these singularities here, and for each singularities enclosing we have a curve C 1. So, these are isolated singularities. So, always we can have we can enclose this by another circles which does not have further singularities. So, these are the circles which encloses all these singularities and having only one singularity is in each circle. And then by the Cauchy theorem, if you remember that this integral over the C f z is nothing but the integral of the sum of all these circles. So, C 1 over C 2 over C n, and then for each we can use that 2 pi I, and then the residue at that z 1 point, here residue at z 2 point, and so on, residue at z n point, or we are talking here n or r. So, this is going to be r, and then here also we can go up to r. So, this is the residue theorem which is very helpful now to evaluate such integrals. The only difficulty that we have to evaluate these residues at different points, but the evaluation of residues in each situation we have already discussed. So, we can go for the evaluation part of the integrals. So, for instance, we want to evaluate this integral e power z minus 1 divided by this z minus 1 and z minus I. So, clearly what we see, and the C here is the absolute value z greater than 2. So, the singular points are z equal to 0, here we will get 1 and then we will get I. So, these are the 3 singular points of this function of this integrand 0, 1 and minus I. So, this is 0 here, and then we have 1 and then we have I there, and this is the circle mod z equal to 2. So, in this case all these singular points are lying inside this circle. So, we have to apply now the residue theorem, meaning we have to compute the residue at all these 3 points, because all are lying inside the circle. So, these are the now for the first one z equal to 0 we are trying to classify. So, we first take just the limit what happen as z goes to 0. So, this is the integrand, exactly the integrand here. So, this has 0 by 0 form, because e power 0 1 minus 1, this is 0, and then here we have also 0. So, 0 by 0 form we can deal with the L'Hopital rule. So, the numerator when we differentiate we will get e power z, and from the denominator when we differentiate the product rule has to be applicable now. So, with respect to the first, this z is differentiated. So, we have the remaining 2, then the z minus 1. So, we have z and z minus I whole square, and then the third one is differentiated. So, we have 2 times and z minus I and z into z minus 1 remain as it is. So, here by doing so, now we can pass the limit, and we observe that this is 1 over minus 1 into minus 1, that is 1. So, the limit here is 1. So, the direct limit is coming as limit z approaches to 0, this is the value is 1 here. That means, this is a removable singularity, z equal to 0 is a removable singularity, is a removable singularity. And now, we will discuss the other one. So, for z minus 1 now, because this can be also observed here, because here the L'Hopital rule was applicable, and as a result finally, we got this value as 1, but this is not going to be the case when z approaches to 1. So, this z minus 1. So, what we are considering now, the limit z approaches to 1 and z minus 1 and the f z, which is the integrand there. So, that means, this z minus 1 will get cancelled from this function, and we have e power z minus 1 z into z minus I square. So, if we take this limit now, so we can substitute directly, and we got this value e minus 1 I by 2 as the value of this limit. So, it is clearly then the z is equal to 1 is a simple pole. So, this another singularity is classified as a simple pole, and similarly we can talk about the z equal to I. So, in this case z minus I the whole square we have to multiply and then take the limit. So, this is going to be a pole of order 2. So, all classification is done here. The z equal to 0 is a removable singularity, the z equal to 1 is a simple pole, and z equal to I is a pole of order 2. So, pole of order 2. Now, for each we have to evaluate the residue. So, in the first case, since it is a removable singularity, the residue is going to be 0. So, removable singularity, there will be no term with having negative powers in the Lorentz series, and therefore, the residue is going to be 0, and the residue at z equal to 1, if we compute now this was a simple pole. So, we have to get basically this limit, this is what we have discussed earlier, z minus 1 f z, and z approaches to 1 we have to evaluate, and this we have evaluated before also. So, it was e minus 1 I by 2 this calculation says. Z equal to I, we know it is a pole of order 2, and then this we have to get this derivative once for this z minus I square f z term, and if we do so, this derivative here of the square means this z minus I square will be removed from this function now. So, e power z minus 1 z z minus 1, we have to get the derivative, and then we have to take the limit at z approaches to I. So, in this case z equal to I, and here this quotient rule will be applicable. So, the square of this, and then we have to differentiate this, that is e power z with z minus 1, and then again e power z minus 1 will remain, and here the derivative will be 2 z minus 1 with minus sign there. So, this is just the quotient rule, the simplification, substituting this limit z equal to I, we are getting this number there. So, which can be further simplified here to get a simple minus 3 I e power I 2 I and then minus 1. So, this is the residue at z equal to I. So, we have these 3 residue, one was 0, the other one e minus 1 I by 2, the third one this one. So, to get the integral value there, so the integral I will be 2 pi I and the sum of all these residues. So, 2 pi I, and then we have 0, the second residue, and this residue of this at the point where it is a pole of order 2. And now, if we just simplify a bit more, we will get this value of the desired integral. So, this was one of the applications which we have seen these residues play an important role for the evaluation of these integrals. Without using the residue, this might be little bit more complicated. So, another example which we will see in this lecture now, we will evaluate this function, this integral, where we have this z 4, 13 z square and 36, and the mod z is pi. So, again we have to look for what are the singular points, and then we have to classify these singular points, and accordingly we have to get the residue and then the residue theorem. So, all these points to be used again. So, the coming to the singularities. So, this is a quadratic equation in Z 2. So, we can just solve it, and what we observe that z square is equal to minus 4, z square is equal to minus 9. These are the two equations coming out for z square. So, that leads to that z is plus minus 2 I and z equal to plus minus 3 I are the zeros of this polynomial which is appearing in the denominator. So, all these points are going to be the singular points for this integrand. So, we have the singularities now 2 I, minus 2 I, 3 I and minus 3 I. These are the 4 singularities, and for each we have to evaluate residue. So, clearly what we will also see here that all these singularities again are coming inside this mod z equal to pi, because pi is more than 3 and now we are going here up to 2 or 3. So, all these singularities are lying inside this circle of radius this pi. And again with now we have the idea, we do not have to check each and every case, because your function is now like z and then cos hyperbolic pi z, and divided by we have the z minus 2 I, then we have z plus 2 I term, we have z minus 3 I term, we have z plus 3 I term. So, these each of them, whether z equal to 2 I or z equal to minus 2 I or z equal to 3 I or z equal to minus 3 I, all these points are simple poles, because if we multiply by z minus 2 I for instance to this f z, here this z minus 2 I, and then take the limit will exist similarly for z plus 2 I and so on. So, all these are simple poles. And now, so the residue, if we want to get for instance z equal to 2 I for this f z, this was f z here. So, we have to multiply by this z minus 2 I and then f z. So, if we do so, we have this result after putting the limit also for this z equal to 2 pi everywhere, and this cos hyperbolic 2 pi I. So, cos hyperbolic 2 pi I by definition we have e power this 2 pi I e power minus 2 pi I divided by 2, and this is nothing but the cos 2 pi which is 1. So, this is 1 there into the 2 I. So, we get, and then here also I get cancelled. So, finally, we are getting this 1 over 10. So, the residue at this z equal to 2 I is 1 over 10, and what we can observe that if we compute the residue at z equal to minus 2 I also, it is coming the same number as 1 over 10. And again if we compute now z equal to 3 I or z equal to minus 3 I, they both are also coming to be exactly equal to 1 over 10. So, all these residues at all these simple poles, the value is 1 over 10. So, we can now evaluate this integral, which is 2 pi I, and the sum of all these residues, which each of them is 1 by 10. So, we have 4 by 10 here, and then 2 pi I. So, the final value of this integral is 4 pi I by 5. So, another example now, here we have this f z, z plus 1 over z 4 minus 2 z cube, and the circle is mod z equal to half. So, now the circle of radius half. So, if we discuss the singularity here, so we have actually z cube and then z minus 2. So, z equal to 2 is a singularity and z equal to 0 is also a singularity. So, these are the two singularities, and we should note that this z equal to 2 here now is outside this z is equal to half. So, at least one of them is outside the circle. So, this is of no concern to us in the residue theorem. Now, we do not have to compute the residue at z equal to 2, we need to just compute the residue at z equal to 0. Okay, so, for z equal to 0, what the function f z is z plus 1, and then we have z cube and z minus 2. So, clearly it is visible here that we have to check with this z cube f z. So, this is going to be a pole of order 3 if this limit exists, and obviously, when z 0, so 1 minus, so minus half is coming there straight away. So, this is a pole of order 3, and then we have to compute the residue for this pole which is of order 3. So, the residue of this f z function at z equal to 0 will be with this formula which we have just derived before, 1 over this m minus 1. So, here 3 minus 1, and then again this m minus 1 at derivative, that is the second derivative, and then the limit z approaches to 0 we have to consider of this function z cube f z. So, here we have 1 by 2 and then this limit. So, the second derivative for this z plus 1 over z minus 2, that is the portion when we multiply this to z cube. So, the z cube get cancelled, and we have to take the double derivative simply for this function. So, the first derivative is given here, then once again we have to first simplify this and then take the derivative again, and finally take the limit. So, it is coming as minus 3 by 8 the residue at z equal to 0. So, the value of this integral is going to 2 pi I, the value of the residue, which is minus 3 by 8. So, the integral value is minus 3 pi I by 4. So, what we have observed that one of the singular points of this f z was outside the region of this integration or this curve. So, we do not have to now compute naturally the residue at this point. So, another example where we have the integrand with the sum of the two functions z e power pi z and then z 4 minus 16, then we have here z and e power pi z, then d z there, and C is a circle with the ellipse which is x square plus this y square by 9 equal to 1 in the standard form. So, this is the ellipse there, and if we look at the first portion here, because of z square minus 16, we have z square is equal to plus minus 4, and therefore, z is plus minus 2 I, and we have plus minus 2. So, these are the 4 points where this function break down these are the singular points, and we can easily see now. So, this is z equal to 2, here we have z equal to minus 2, then we have z equal to 2 I, and then we have z equal to minus 2 I, all these points, and there is another point here z equal to 0, that is also a singular point of this f z of this integrand, because we have e power pi over z, and as z goes to 0, we have here infinity and everything goes to infinity now. So, that is also the function is not defined. So, that is also a singular point. So, we have several singular points here 0, plus minus 2 I and plus minus 2 all are here. These two they lie outside because z equal to 2, and here this distance is coming as 1 only. So, this is outside the domain. So, therefore, these two will not be considered. We have the 3 points where the residue has to be evaluated. Okay. So, first for the first function, this z e power pi z over z square minus the 16. So, if we compute the residue there at z equal to this 2 I and z equal to 2 I. So, z plus 2 I is z square minus 4. So, except this z minus 2 I term, the rest is considered here, and then we will get this limit z equal to 2 I, we got minus 1 over 16. Similarly, for minus 2 I also we can evaluate this, and the same number minus 1 over 16 will come. So, these are the 2 points there we have evaluated. Z equal to 0 also we have to see what is, which is appearing in the second term, and this is an essential singularity, as we have seen it is appearing in e power pi z. So, we have z, and then we have the expansion for e power pi z. So, finally, this is the expansion for this given function, and as far as this 1 over z is concerned, this is the coefficient here for 1 over z, and therefore, the residue of this function z e power pi z is pi square by 2, because this is going to be the b 1 term, the first term where the negative power starts. So, this is the first term 1 over z, and this is 1 over factorial 2 pi square, that is the residue we have, and the integral, then this integral which is to be evaluated now. So, we have 2 pi I, the sum of those two residues, and then the third one here where the function is having essential singularity pi square by 2. So, this adds to this pi square minus 1 by 4 and I. So, that was the example where we have also considered one of the singular point as essential singularity, and now these are the references we have used for preparing this lecture. Just to conclude, so we have discussed the residue theorem, which is simple, that 2 pi I and the sum of the residues we have to consider, and these points are the singular points z k point, which lies inside this boundary C. Residue at a simple pole can be easily computed by just taking this limit z minus z naught and f z. If it is a pole of order m, then we have to take this m minus 1th derivative of this function z minus z naught power m f z, and then take the limit. Also, we have to divide this 1 over factorial m minus 1. If it is essential singular points, we have to use the Lorentz series expansion, and then we can find the coefficient of this first term where the negative powers starts. So, that is all for this lecture, and I thank you very much for your attention.